All right, I think we're ready to get started. So the first thing we want to do is get this chapter 3 problem set done. And so this one involves exclusively complex numbers. When this is done, we can get back and finish chapter 3, which we were not completely done with. And then what we can do is there's a second chapter 3 practice problem set, which we can then do. This one we're not 100%, well, maybe we are, but we'll finish up chapter 3b first before we get to this one. And then we can start chapter 4, which we haven't looked at yet. That would be our discussion about logarithmic and exponential functions. Now, also, I just want to point out, let's go back to Moodle for a second. Let's see. Okay, here we go. So anyway, what I put up here, I'm sorry, it's not there yet. I'm still working on it. There is going to be a midterm sooner or later. Of course, we have to have one. The first midterm for this class will be based on chapters 1 through 3, which means we're just about ready. So what we have to do is wrap up all the practice problems. And then I'm still almost done with it, not quite there. There's going to be a sample midterm that you can practice with. It basically covers everything we've done from chapters 1 through 3. And then we will do that next week. And when that's done, then you can actually do the real midterm. Now, the midterm will be done on a take-home basis, of course. And so you'll have a week to do it. And it'll be just exactly what we've been doing all along. There'll be no surprises. So both of those will be ready very soon, in a day or two. So for today, we'll wrap up chapter 3. We'll do the 2 problem sets. And if there's time, we'll start chapter 4. But then next week, we'll do the sample midterm. And then I can just post the midterm, and you can finish that in about a week or so. All right. So that's where we're going. So finally, at long last, we're just about ready to have an actual test. I'm sure this class is the last of your classes to give you a midterm. You probably have already had one in your other classes. So, but don't worry, you'll have plenty of time to finish it. And the only thing we have to do is, and we'll discuss this next week, because it's a math test, you can't realistically type it up unless you're really good with the equation editor. And so what I normally have people do is just draw it out on a piece of paper like you would in a normal classroom setting, and then just take pictures of it with your camera phone, or else use a scanner for it, and then send it back to me by email. It seems to work pretty well. As long as you're careful when you take pictures, just make sure that everything on the page is legible. You shouldn't assume that it is, because it's not quite the same thing as taking pictures of kittens and things like that. You want to just make sure that everything is clear and legible when you send it back. Most people don't have a problem with that, but occasionally I run into ones that are just completely unreadable. All right, but again, we'll discuss this again next week when we're going over the sample midterm. So this way, I just want to let you know where we're going in the next couple of weeks. All right, so in the meantime, let's get back to it. Let's get out this chapter 3 problem set and start working on it. And this is number 1, actually. There's 2 of them. We'll start with the first one again. This we've already definitely covered. This is our discussion about imaginary numbers. And we know that imaginary numbers are very important and useful. We got to see that long series about the history of the development of imaginary numbers, which I think you'll agree was quite interesting. But right now, we just want to remember the important properties of imaginary numbers and be able to do some algebra with them. All right, so let's start at the beginning here. So for example, let's look at this first one. Now, of course, when you see the word evaluate like this, what it means is basically replace every x with, in this case, 2i. All right, so evaluate simply means substitute a specific value into the equation for x. So here, for example, we're going to have f of 2i equals 2i squared plus 2i, whoops, 2i minus 4. Now, this is the trick. The key to the whole thing, you might recall, in fact, why don't we go back and revisit the notes for a second. The challenge here is the exponents of I. Remember, there's a cycle to them that we want to take advantage of. All right, so let's go back. And summary, here it is. So you might recall that I squared is -1, I cubed is -I4 is 1, and then when we get to the higher powers, this cycle just continuously repeats itself. In other words, I to the 5th is -1. I to the 5th is I to the 6th is -1, just like I squared. I to the 7th is -I, like I cubed. And I to the 8th is the same as I to the 4th, which is 1. So here, in this example, on our problem set, this 2i squared actually becomes 4i squared plus 2i minus 4. All right, so once again, because I squared, according to our results here, is -1, that means we can replace this I squared with -1. And so you can see you're going to get -4 plus 2i minus 4. And the final result will be, and by the way, in cases like this, what we typically try to do is put the real numbers first, and then all the i's will come second. In other words, this is how we normally write an expression like this. -8 plus 2i is the traditional form for writing out what we will call complex numbers. So you might recall a complex number. It takes the form a plus bi, okay? So in other words, I itself is an imaginary number, but when we combine it with real numbers, we call it a complex number. Now, it doesn't ask you that, but I just wanted to remind you of that. Now, if you wrote down 2i minus 8, of course, that's not wrong, but this is the preferred way of writing it. Okay, mathematicians are very particular about certain things, especially the way expressions are written. Now here, remember what we're going to do is simply replace all the x's with i's. And so I cubed, let's go back to our list here, is -I. Okay, so we'll have -I minus 2. And although we should theoretically rewrite this as -2 minus I, we're done. Just because, again, this is the preferred form for complex numbers. All right, so there's nothing wrong with this one, but this is the way we normally like to see it. Okay, so you can see they're all going to be very similar. Now, this is where it starts to get a little trickier because you've got a binomial expression in the parentheses, so you're going to have to square the whole thing with this term right here. All right, so let's do this. All right, now the 2 plus I squared, we can actually solve this with FOIL. Let's try that. You don't really have to, but I think it might be a good idea. It certainly helps reduce the risk of mistakes if we apply FOIL here. Okay. So in this case, let's write this as 2 plus I and 2 plus I. And so F is clearly the 2 times 2. O would be these two. This would be I, and this is L. All right, so for F, we're getting 4. For O, we're getting 2i. For the inner, we're getting 2i again. And for the last, we're getting I squared. All right, so when we consolidate these, we're just reminding ourselves this is 2 plus I squared. Therefore equals 4 plus 4i plus I squared. But remember, I squared is simply -1. So we end up with 3 plus 4i for this part of the expression. All right, the rest of it is pretty straightforward. So we end up with 3 plus 4i. Now here we multiply 3 by all the terms inside the parentheses. So we have plus 6 plus 3i plus 5. And now we can just consolidate them. The constants, we have 3 plus 6 plus 5 plus 4i plus 3i. And so when we're done, we end up with 14 plus 7i. All right. And then we're done. All right. Now here's one. Again, we have to square one of these terms. F of 2 minus 3i is 2 times 2 minus 3i squared plus 2 minus 3i minus x. And once again, what we may want to do, just to be on the safe side, is take this piece, just the binary, this expression rather, the squared expression, and figure it out from FOIL. Otherwise, it might be, let's face it, it's very easy to make mistakes with these expressions. So the more systematic we can be, probably the better off we are. So what do we have here? F O I and last. Okay, so let me move these down. Hold on a second. Okay, so F would be 4. O is minus 6i. I is minus 6i. And L is positive 9i squared. All right, so therefore, this expression equals 4 minus 12i plus 9i squared. But, of course, we know I squared is -1. So we have 4 minus 12i minus 9 equals minus 5 plus 12i. So when we come back here, that means that we can replace just this piece with this. All right. Oh, now what happened here? Where did that x come from? Oops. Oh, I just realized this. This was supposed to be there. No. Wait a minute. What did I do? That's a 3. Sorry. There's a typo in here. Yeah, it's 2x squared plus x minus 3. Yeah, that's better. All right. All right. So once again, it's 2x squared plus x minus 3. Now we're good. All right. So what I'm going to do is replace everything in the right here. This expression becomes this. So we have to be careful because we still have to multiply all that by 2. All right, so we have equals -10 plus 24i plus 2, plus 2 minus 3i minus 3. Now it's just a question of consolidating all the constants. -10 plus 2 minus 3 plus 24i minus 3i. And therefore, when we're done, it looks like we have minus 11 plus 21i. 21i. Okay, that's better. Now, did I do that right? Let me just double check. It's so easy to mess this thing up. Let me just confirm this. So you've got 4 minus 6 plus 9. That's no problem. All right, so we plug this in. Okay, it looks good. Okay. Now this one's going to be a bit of a mess, but not really, because it enables us to take advantage of a technique we saw in the chapter. So first, let's just plug everything in. So remember, each x becomes 5i. And you might say, well, we're done. And, we are, and yet we're not, okay? Because this is not the form that we prefer. Remember, we decided somewhere along the way that we would prefer not to have imaginary numbers in the denominator. So what do we do about it? Well, here's what we can do. We can use the so-called complex conjugate technique. So just recall, the complex conjugate of a plus bi is a minus bi. So how does that help us? In fact, why don't we go back to that section of the chapter and revisit this idea for a second. This is our discussion about division. And so the idea here is that in order to get rid of the complex number in the denominator, we multiply the entire expression by the ratio of the complex conjugate of the denominator over itself. And when we're done, we should wind up with a number that has just real numbers in the denominator. So let's see how that would work. So in other words, what I'd propose to do here is take this number and multiply it. As soon as this thing wakes up, here we go, by the ratio of 2 plus 5i, 2 plus 5i. And now, of course, because I'm multiplying by a ratio which equals 1, I haven't changed anything. But now I've got to watch it because I need to do some foiling here for both the numerator and the denominator. Okay, so the numerator is 5i plus 1 times 2 plus 5i. And so if I apply FOIL here, what should I get? F, O, I, and L. So F is 10i. Whoops, no caps, it's I, lowercase I. Outer is 25i squared. Inner is 2, and last is 5i. Okay, so this equals, so we bring them together. Now you can see we've got some repeated terms. And so we can write this as, oh, wait a minute. Well, look what we have here. We have an I squared. So we can actually replace that with -1. So we've got 10i minus 25 plus 2 plus 5i. And when we're done here, what does that give us? Minus 23 plus 15i. Okay, perfect. So the numerator of this expression is minus, so that, let's summarize this. The numerator equals -23 plus 15i. Now for the denominator, we have 2 minus 5i. Now the denominator should be easy. It's designed to be easy. That's why we chose that particular multiplication. And when we're done, there should not be any imaginary or complex numbers in the denominator. This is done by design. So again, we have first, outer, inner, and last. So 4 outer would be 10i, inner would be -10i, so those will cancel out, and last would be -25i squared. Okay, so let's bring those together. So that reduces very nicely to 4 minus 25i squared, but of course 25i squared means there's a -1 in there. All right, hold on a second. All right, so we got 4 minus 25 times -1, and that means we've got 4 minus 20 plus 25, 29. Okay, so the denominator is 29. And so finally, when the dust settles, our result is, let's put this in the equation editor because it's a ratio. We have in the numerator minus 23 plus 15i, all divided by 29. All right, so finally, at long last, we have a result. So that was a bit of a mess. Oh no, it doesn't completely cancel. It just gets rid of the imaginary numbers. That's the only reason that we do it this way. So no, it doesn't work that way typically. We just end up with a real number. That's the only thing we can hope for. We don't necessarily eliminate everything. In fact, if we did, we'd end up with 0 in the denominator anyway. So instead, what we're hoping for is to reduce everything in the denominator to a real number. So it's just simplification. That's literally all that it is. Okay. All right. Now the next one is the same. Similar, I mean. Now maybe it's a little bit less messy. So we're replacing all the x's here with 4i. So let's see what happens then. Okay, so f of 4i is now equal to so this x becomes 4i. And so we end up with 1 plus 8i is divided by Now here, I'm just going to rewrite it slightly. It's 3 plus 4. I just want to make sure that it's written in the proper form. And in other words, have the real number first and the imaginary number second. And once again, what we would like to do is multiply this by its, the ratio of the complex conjugates. All right, let's give this thing a minute. There we go. All right, so we have this expression. So the complex conjugate of the denominator is equal to 3 minus 4i over 3 minus 4i. Okay. And once again, we would like to do apply FOIL to both of them. So anyway, so first would be 3, O would be negative 4i, L would be minus 32i squared. Wait, oh, wait a minute, sorry. What did I do? First, I think I messed it up. F O I would be right here. Oh, I see what I did. All right, it's just minus 24i. And then finally last, and oh no, that's right, it's positive. 8i times 3 is, of course, 24i. Last is minus 32i. That's it. Squared. Okay, now we're good. So anyway, this equals 3 minus or plus 20i minus 32i squared. Now, of course, that means we can get rid of that I squared because it's just negative 1. All right, hold on one second. All right, that's better. All right, so we've got 3 plus 20i plus 32 because these two negatives cancel each other out. So we've got 35 plus 20i in the numerator. And then in the denominator, we have, now here, it should get simpler. And the reason why it's getting simpler is because O and I will cancel each other out. That's really the bottom line. Okay, that's why this is happening. All right, this is our F, O, I, and let's give this a little more room here. Hold on. Let's try that again. F, O, I, and L. So we have for F, 9, O would be minus 12i, I would be positive 12i, so they will cancel out, and L is minus 16i squared. All right, so when we bring these together, we have 9 minus 12i plus 12i minus 16i squared. And of course, I squared drops out. or it doesn't drop out. It reduces to -1. So we've got 9 minus 16i squared. 9 minus 16 times -1, 9 plus 16, 25. All right, so we've got our numerator, we have our denominator, and so our final result, wow. Now this one is interesting because we can probably simplify it just a little bit further. You'll see why in a second. So we've gotten in the numerator 35 plus 20i. In the denominator, we had 25. Now, the reason why this is interesting is because these are all multiples of 5. So you can take it one more step. And this is as simple as it's going to get. This is the final result. There's nothing you can do to make this any simpler. So that is considered to be the final answer. All right, now if you left it like this over here, that's fine. But if you noticed it, you should divide out. You should actually simplify whenever possible. That's the rule for math. Always simplify whenever possible. All right, now what about these? Okay, well now these are actually, by comparison, these are a lot simpler because you're just adding and subtracting. So here, for example, you'll have 3 plus equals 3 plus 2i plus 5 minus 3i. And when you consolidate these, you'll just end up with 8 minus I. Oh man, that's so easy. We like easy. Okay, all right, let's see what's next. So now here, minus 2 minus 4i plus 1 plus 6i. Now, again, when you consolidate the constants, you get minus 1 plus 2i. And that's it, you're done. All right. Now here you have minus 5 plus 3i minus 6 plus I is minus 11. And then we have plus 4i. All right, now here we have 2 minus 3i minus 3 minus 2i. Now remember, you have to be careful here. You're subtracting this entire term, so both of these become negatives. And so when you bring together the constants, you should have minus 1 minus 5i, and you're done. All right, now how about here? Minus 4 plus 4i minus, now this is a minus 6, minus a minus 6, it becomes plus 6. Then we have minus 9i when you apply this negative to both terms. So you should have 2 minus 5i. Oops. 2 minus 5i, there we go. Okay, now this one, these are products and ratios. All right, that's good. So here, for example, you're using the distributive property to multiply 2 times 4i plus 3i times 4i equals 8i plus 12i squared. And of course, we don't want to just leave it like this because we know that 12i squared, I squared is negative 1. And again, once we may as well rewrite it in the proper format. Negative 12 plus 8i. All right, not that there's anything wrong with this, but this is the preferred format. All right, so I won't take points off for trivial things like that, but just in general, you know, you want to be careful with these expressions. All right, now how about this one? It's a very similar one. Okay, so what happens here is we're multiplying these terms by 3i, so you'll have 5 times 3i minus, or plus, let's do it this way, plus, or no, we can write it like this, minus 2i times 3i. 15i minus 6i squared is 15i minus 6 times negative 1, 15i plus 6, or 6 plus 15i. All right. Okay, here we go. Now we've got another FOIL. Now we've had plenty of practice with FOILs this morning, so we should have no trouble with this one. All right. F, O, I, and L. So F is 8. O is negative 2i. I is 12i. What the hell happened there? And then we have minus 3i squared. All right. So bring them together. 8 minus 2i plus 12i minus 3i squared. 8. Now here we consolidate the two terms in the middle, plus 12i minus 3i squared. And now, of course, 3i squared is negative 1. So we have 8 plus 10i plus 3, or finally 11 plus 10i. Very good. Now this one looks like trouble. Look at all those negatives. It's still a FOIL, but you can see that, well, we just have to be careful. F, O, I, and L. Okay, so let's see what we get. So the F is positive 2. O is negative 3i. The I is minus 4i. And then finally the last is 6i squared. And so when we bring them together, we get 2 minus 7i plus 6i squared equals 2 minus 7i plus 6 times negative 1. It's 2 minus 7i minus 6. So we have minus 4 minus 7i. Very good. Now, this next one is also FOIL, but if you notice very carefully, we've got two terms, one of which is the complex conjugate of the other one. So this one should reduce to something fairly simple. So, well, let's see how it goes. We've got F, usual F, O, I, and finally L. So F is 16, O is 8i, I is negative 8i. See, those two will cancel out, and L will be minus 4i squared. All right, so when we bring these together, we'll have 16 plus 8i minus 8i minus 4i squared, or 16 minus 4i squared. And of course, that I squared can be replaced with negative 1. Oh boy, that's simple. That all turns out to be 20. How do you like that? No complex numbers at all, no imaginary numbers. It's just 20. And so when we did our ratios, of course, this is the purpose of multiplying by a complex conjugate, so that the denominator would be guaranteed to be a constant, a real number rather than an imaginary number. So we should not be surprised to see this. Okay, now with these, of course, this one means, with something like this, we need to multiply it by its own complex conjugate, unless we can reduce it further, which is actually not the case here. If we could, we would, but instead, what we're going to do is put the ratio here of 2 plus I over 2 plus I. All right. So now, unfortunately, that means 2 more foils, but all right, we can do it. So for the first one, we have 3i, 2 plus I. All right, so let's do a FOIL on it. F, O, I, and L is 6 for F. O is 3i. I is 8i. And then finally, last is 4i squared. Here we go. All right, so what does that give us? 6 plus 11i plus 4i squared. And of course, that last piece will be replaced. That I squared is negative 1. So we've got 6 plus 11i minus 4 equals 2 plus 11i. That's the numerator. Now we still have a denominator to deal with. And let's try that. And so, what do we have? O, I, L. All right. So that means we have F would be 4. O would be 2i. I would be negative 2i. And that's, of course, because they're complex conjugates of each other. We'd expect to see some canceling. All right, so this entire expression equals 4 minus I squared. The O and the I both cancel out. So we have 4 minus 1 equals 4 plus 1, which is 5. So then we have our numerator, we have our denominator. We'll bring them together. All right, so the ratio of the final result, after all that work, is 2 plus 11I all over 5. And we're done. So by now, I think we're getting pretty good at this. So number 18 is next. And so we're going to do the same thing. And let's see what happens here. Then the next two get even a little bit messier. All right, so here we again want to do multiply by the ratio of the complex conjugates. And let's see what happens then. 2 plus 3I over 2 plus 3I. And now, once again, we have a couple of foils in our hands. All right, let's see what happens then. All right, so for the numerator, we have 2 plus 3I, 2 plus 3I. So, of course, you're basically squaring this 2 plus 3I, but let's see how that works out. There won't be any cancellations here because there's no negatives. So we're going to have 4 for F. O is 6I, as is I. And the last term is 6I squared. No, sorry, it's 9I squared. All right, so we'll bring them together. 9I squared, 4 plus 12I, plus 9 times negative 1. 4 plus 12I. 4 plus 12I minus 9 equals minus 5 plus 12I. Fine. The denominator is the one that should be simplified. 2 minus 3I, 2 plus 3I. All right, and we'll see how that works.
What?
F O I L. All right, let's see what we get. All right, so F is 4, O is 6I, I is negative 6I, and L is minus 9I squared. So this time, though, the I and the O and the I terms do drop out. All right. So we'll have 4 plus 6I minus 6I minus 9I squared. 4 minus 9I squared. Okay, 4 minus 9 times negative 1. 4 plus 9 equals 13. All right, so when we're done, we've got a ratio of a complex number to a constant. And let's see, what does that give us? That would be the ratio of negative 5 plus 12I all over 13. That's it, and we're done. Okay. Actually, let me leave in the equal signs.
Holy fuck.
Now, this one's a little different because we've got a product in the numerator. What we probably should do before we go any further is multiply out the numerator with FOIL. Okay. So then we can decide what to do next. All right. So let's do this. So in the numerator, 2 plus I, 4 minus 2I. So again, we'll apply FOIL. All right, so once again, here's F, here's O, here's I, here's L. And so let's try this. F is 8, O is negative 4I. Oops. I is positive 4I. And finally, we have minus 2I squared. All right. 8. Now, this is just a coincidence that these two cancel out because those are not complex conjugates of each other, but it happens like that way sometimes. So we just have 8 minus 2I squared. And of course, that I squared is replaced with negative 1. So the numerator, oh, look at that. Now, you know what? That's a very good result because now what we're going to do is rewrite this expression. Wow, but that turned out well. Not that we're done, but we can rewrite this as 10 over 1 plus I. Now, the next step is then to multiply by the ratio of the complex conjugate in the denominator. Hold on one second. So that would be the next step. But you see, by multiplying out the numerator first, we really made things a lot simpler. All right, so here, we're going to multiply this by the ratio of 1 minus I over 1 minus I, of course. Now, the numerator is easy. This is just going to give us 10 minus 10I. The denominator is a case for FOIL, of course. And so, let's see, F, O, I, L. And now F is just 1. O is negative I. I is positive I. Inner, that is positive I. And last is negative I squared. So we have 1 minus I plus I minus I squared equals 1 minus I squared. And of course, I squared is negative 1. So we have minus a minus 1, which means we have 1 plus 1, which is 2. Okay, so the numerator is 10 minus 10I. The denominator is 2. So if we go all the way back to the start, this messy looking expression is actually not that bad because we actually wind up with In the numerator, we can reduce that to 10 minus 10i. In the denominator, we just have 2. So look how easy this is, because this reduces to 5 minus 5i, and we're done. Ooh, that worked out rather well, I must say. Who would have thought that that would reduce to something so simple? All right, and then there's one more, and then we're done. By now, we're basically experts on complex numbers. So let's try this one. We'll do the same approach. We'll start out by using FOIL in the numerator, because we may be able to reduce it to something much simpler. All right, simplification is always something we want to do whenever possible. All right, so of course this one requires FOIL. Beautiful. Okay, now, so let's do this. F is 2. O is 4i. I is 6i. And L is negative 12i squared. All right, 2, negative 4i, 6i, and minus 12i. All right, perfect. So we have 2 minus 4i plus 6i minus 12i squared. 2 plus 2i minus 12i squared. Oops. 2 plus 2i minus 12 times negative 1 plus 2i plus 12 is 14 plus 2i. So it's not that simple, but all right. And the denominator is 1 plus 2i. There isn't anything we can really do with that. So our original expression, though, can be rewritten in a slightly simpler form, which is really all we can ask for. (14 plus 2i). In the denominator, it's 1 plus 2i. All right, now this means that we're going to go ahead and use the complex conjugates. All right, the final result may not be like as easy as the last one, but still, we can definitely work on this a little further. All right, so of course that means we're going to multiply by the ratio of 1 minus 2i over 1 minus 2i. And now, sadly enough, we have to do 2 more FOILs. Our work is never done here, is it? No. All right, let's try that. All right, so here's the F, O, I, and L. All right, so F is 14, O is minus 28i, I is 2i, and L is minus 4i squared. So then we'll have 14 minus 26i minus 4i squared. 14 minus 26i minus 4 times minus 1. 14 minus 26i plus 4, 18 minus 26i. All right, the denominator is 1 plus 2i. There we go. 1 minus 2i. All right, so once again, we're going to use FOIL, but this time, because we're multiplying a number by its own complex conjugate, we should get some simplification here. It should reduce to a single constant, a real number. Okay, so it's getting a little sloppy in there, but f is 1, o is negative 2i, I is positive 2i. And L is negative 4i squared, yes. So we have 1 minus 2i plus 2i minus 4i squared. 1 minus 4i squared. And finally, 1 plus 4 equals 5. Beautiful. So as we predicted, this one, the denominator is a real number. So the bottom line is that we end up with a ratio of 18 minus 26i in the numerator. And then we're going to divide that by 5. All right, and then we're done. Okay, well, it doesn't seem very much simpler, but that is the result of, yeah, it's simpler. It's definitely simpler. This is what it used to look like. So now we have this, and that's our final result. So finally, at long last, that one's done. Now, now we can go back to the chapter 3, because we're not completely done with it. And when that's done, we can tackle the second chapter 3 problem set. Okay, we don't want to do it just yet because we're not completely done with the chapter, but as soon as we are, we can go through that. And then if there's still any time left, we can at least take a peek at chapter 4. All right, so let me, of course, as usual, the solutions here will get posted on Moodle, so you can download them and double check them and make sure you've done everything correctly. Let me just do one thing here. This is one of the annoying things about Word. It doesn't automatically give you page numbers unless you ask for them. I don't understand their reasoning there. I would think that everybody would want page numbers, especially for a long document, but no, you have to do it yourself. It's really stupid. All right, so that's it. We're done here. All right, good. Now let's get back to this discussion. And as far as no, not this section. This is 3A. There's a 3A and there's a 3B. This is 3B. All right, so we're getting close to the end here. What we're doing is looking at different techniques for solving polynomials. If you recall, a polynomial, let's go back to the beginning here, is simply an expression that has many, many terms. I mean, really, that's what it means. An expression with many terms in it. So this is a classic example of a polynomial. It can have any number of terms that we like. So you'll notice that the way it's written, the exponents start with n, and they work their way down, n minus 1, n minus 2. Down here, the exponent for x here is actually 1, and then 0 here. The coefficient is labeled accordingly. And so what will happen is each function that you'll encounter is a special case of this particular expression. In other words, a linear function is a polynomial of degree 1. That would be this one. So basically what I did was I went back here and we start with A1 and then we ignore all the rest of these. These can be thought of as zeros. For quadratic, using the same notation, you would have a2 x squared plus a1x plus a0. And again, you're just coming back here and, basically dropping out everything above 2. All right. And then for a cubic function, you can probably guess what's coming now. We'll have a3 cubed, a2x squared, a1x plus a0. And it just keeps going up. The next one would be called quartic, and they all actually have names, all the way up to maybe 10. You don't usually hear them very often. What we often do instead is refer to these functions by their order. So for example, this equation here is said to be of order 1. This is order 2. And here it says it's said to be of order 3. And the order simply means the highest exponent in the function. So here, by the way, don't forget there's an implicit 1 here. So the highest exponent for x is 1. Here, the highest exponent for x is 2. And the highest exponent for x is 3 down here. So this cubic function is actually a polynomial of order 3 or degree 3. Both of them mean the same thing. Down here, we have quadratic. It's either of degree 2 or order 2 because we have an x squared term. And up here, we have degree 1 or order 1 because there's an x1 to the first power here. So the polynomial expression here actually shows all the different cases we might encounter. And the functions that we tend to work with are typically special cases of this expression. All right, so now with all that being said, so we can go through and identify these. Now, by the way, if you do have an equation where we have an exponent which is not a natural number, meaning 0, 1, 2, 3, 4, 5, 6, 7. This one, for example, is not considered to be a polynomial because it has this x to the minus 2 power in it. So for a polynomial, the exponents are restricted to 0, 1, 2, 3, 4, et cetera, et cetera. In fact, let me make a separate note of that. Right, okay, let me just throw that in here. Polynomials, whoops. Yes, we are, don't you worry, we'll be doing that. Okay, so polynomials are restricted to exponents that are natural numbers. And the natural numbers that's just a set that contains 0, 1, 2, 3, 4. In other words, it's basically all the positive integers plus 0. If you have anything else in there, then it is not a polynomial. It has a different name. It is not a polynomial. All right, so then we went ahead and we were looking at the degree or order. Like I said, is simply the highest exponent in that expression. The leading coefficient then, oh, by the way, yes, so here's some more terminology that we need to know. So not only are these of degree or order 4, 7, and 5, sorry about that. This is considered to be the leading term. Okay, it just means it's the term with the highest exponent in it. And then the leading coefficient is just the coefficients. In other words, here, this 5 is the leading coefficient. And you can kind of start to see here why it's so important to write these expressions with the highest exponent first, because that has a significant role. 5x to the 4th is the leading term, and 5 is the leading coefficient. And on top of that, the degree or order is 4. So all this important information comes from this term. So that's why we really should ideally write this first so that we can find it more quickly and easily and not make mistakes. All right. So again, one more reason why you should, follow the standard formats when you write out these complicated expressions. All right. So now what we were doing, we spent a lot of time dividing polynomials, right? We're not going to do that again today. At least not right this minute. We'll probably see that on the practice problems, but we went through a bunch of divisions. And let's see, what did we do? We looked at the remainder theorem. So we'll skip over that for now. And I'm pretty sure we did the factor theorem. I think the only thing that we really didn't get to was the rational zero theorem, which is, I remember, okay, because this is a fairly complicated idea. And what it essentially is doing is saying, listen, if you've got a very large, messy polynomial, you may want to have some idea of what kind of solutions are possible. Because, let's face it, some of these higher order equations are quite challenging. And so this basically is telling us that if you have an expression like, a standard polynomial, assuming that the coefficients are integers, we're going to define the letter P to represent P is a factor of A0. And Q is a factor, and A0, by the way, is the constant in the equation. Q is a factor of the leading coefficient. Now, sometimes that can help reduce the number of possibilities by quite a bit. And sometimes not, okay? So basically, it's just a way of saying, listen, no matter how many solutions there are, we know for a fact that the ratio P over Q is going to be a solution where P must be a factor of A0 and Q is a factor of whatever the leading coefficient is, which in this case would be here, AN. Now, let me just quickly remind you what it means to be a factor. Let me just throw that in here. Just in case that word, you've forgotten what it means. Let's say for any real number, let's just call it K. A factor is a number. Actually, it's a natural number, or it's a natural number that evenly divides into K. Now, what exactly does that mean? For example, the factors of 10 are 1 and 10 and 2 and 5. Okay, so in other words, altogether, 10 has the factors 1, 2, 5, and 10. So I wrote it that way for a reason. So you can see that they are factors because the product of 1 and 10 is 10. The product of 2 and 5 is 5. So therefore, we can make the case that all 4 of these numbers are factors of 10. If I try to divide any of them into 10, I will get an integer with no remainder. And therefore, 1, 2, 5, and 10 are defined as the factors of 10. Okay, 1, 2, 5, and 10. So that's what this is all about. Also, you might remember one of the movies that we saw, one of the videos guaranteed that a polynomial, and this is something I just want to throw it in here just as a reminder, a polynomial of order n or degree n is guaranteed to have n solutions or zeros, although some of them may be complex. Okay, so remember Karl Gauss's famous theorem, the fundamental theorem of algebra, I think it was called, is the idea that if a polynomial has order n, it's guaranteed to have that many solutions, although it's possible that some of them are imaginary. It's also possible that some of them are repeated. Oh, all right. Let's go back here. If the coefficients are all integers, then now keep in mind the 0 means solution. So if you can visualize, A0 can have a number of different factors, and the leading coefficient, AN, also may have multiple factors. So suppose it turns out that the factors of A0 are, let's just keep it very simple, are just 1 and 2. All right, let's just make up an example right now. In fact, let me jump ahead to a new slide because it's so, I have no space here. All right, so let's just say, suppose that the factors, or how about this, to make it even simpler, suppose that A0 is 2. The factors are 1 and 2. Okay. Yeah, doing subscripts in PowerPoint is kind of a nuisance. And suppose that the fact that AN is 3. And by the way, when we've done a few of these, you'll see what I mean. Therefore, the factors are 1 and 3. Now, P and Q, therefore, P can take on 1 or 2, because those are the factors of A0. Q can be 1 or 3. Therefore, based on this result, since this is true, let's just put this back here so you can see it again. The solutions or roots or zeros must be, all right, now remember, we're looking for P over Q. So basically, all we have to do is go through all the combinations of P and Q. We can have 1 over 1, 1 over 3, 2 over 1, 2 over 3. All right, so in other words, all I did was I took, for P equals 1, I divided it by Q equals 1 and Q equals 3 to get these two. And then I used P equals 2 in these two cases, 2 over 1 and 2 over 3. So what I've done is I've guaranteed, and let me just simplify this a little, that the solutions are 1, a third, 2, and 2/3. And that's it, I'm done. So just make sure all I did, since there's 2 P's and 2 Q's, there must be 4 different ratios that I can form from those choices. All right. So again, all I did was I took the 1 for P in these two cases, and here I set P equal to 2. And then for each P, I try both Q's, which are 1 and 3. And the ratios of those two are the numbers that must be my solution. So I'm guaranteed here to have 4 solutions. 1, 1/3, 2, and 2/3. Now, if you want to double check, you can plug them back into the original equation, and these numbers will give us 0. Okay, so whatever this polynomial is, this means, and let me just copy these again so you can see them. What this is telling me is that whatever the function is, which we don't know because I just made all this up, f of 1 equals 0, f of 1/3 equals 0, f of 2 equals 0, and f of 2/3 equals 0. That's what it means for them to be solutions. So because there's 4 solutions, then this is most likely a quartic function. It crosses the horizontal axis 4 times at those points. That's what this is telling us. Now, the only problem with this theorem is that the number of possibilities can get really large in a hurry. Oh, you know what I just realized? I think I've made a mistake here. I said here the solution 0 is must be. It doesn't, no, must be one of. All right, sorry about that. In other words, the solutions aren't guaranteed. All right, my mistake. Let me fix this. It's not that these are all guaranteed to be solutions, that we're guaranteed that the solutions are in this group. That's what it is. AM, what does AM stand for? All right, so yeah, so what AM, I don't know that. What does AM stand for?
I don't remember what AM stood for, but like A would be the leading coefficient, and then you'd have to find out what 2 numbers add to a certain number, but multiply to a certain number to get your answer when factoring.
Well, is that only for certain cases, or is that always true?
I think it's always true.
All right, well, you know what? Why don't we do this? Let's look in the internet. Well, let's see. Well, if this works, then you should use it. I honestly have never heard of this before. But you know what's funny? Why don't they tell me what AM stands for? It's almost like they don't care. AM.
Oh, I think it's just add and multiply.
Oh.
Yeah, I just figured
No,
it out.
but I mean, why don't they just say that?
I have no idea.
And look, there's an AC method. What is that? I have no idea. The AC method, but this one apparently only works for trinomials. Boy, that looks like a lot of work. I don't know. You know, I have a feeling that what must have happened is somebody sat down and invented these techniques that are meant for very specific cases. That you're, oh, look at this, the lazy AC method. I like the sound of that. But these are shortcuts, and that's nice. If you know how to do this, you go right ahead and do it. I'm just not familiar with those techniques. I think what's happening here is that this discussion we're having here, this is meant to represent the most general possible case. In other words, this is something that would always, always, always work. And so mathematicians, they like to start out with the most general cases. They want to prove a result that always works. And then if you can find a quicker way of doing a specific case, that's fine. But they would prefer to just do the full-blown approach first. So yeah, I just realized my mistake here. The solutions are not guaranteed to be all of these, but at least one of these. All right, so let's rewrite that. It must be one or more of these. So it could be the case that these are all solutions, but there may be one that's not. So, all right, anyway, so let's just take a look at an example. Once you've done an example, you'll say, oh, okay, this isn't such a bad thing. All right. May not be your favorite technique, but at least it helps us eliminate a lot of possibilities. In other words, if you know for a fact that your solution is either potentially 1, 2, 3, or 4, then rather than messing around looking for, like here's a perfect example. This is a cubic equation. Factoring it out is going to be a major headache. If you could do that, well, then you'd be fine. You'd be all set. You'd set each factor individually equal to 0. But what if you're finding that difficult? It's not like the quadratic formula that can apply to a quadratic equation. I don't think there's an equivalent formula for cubic equations. So what they want you to do instead is say this. This is A0. Now, remember, the way that we wrote this earlier is that f of x, I think this is a n x to the n, so this is actually what we're going to call A3, A2. So what we're focused on is the 2 and the 1, okay? Because this is the leading coefficient. And this is the constant of the equation. The leading coefficient is Q. This is P. So what they're saying, now we got lucky here because 1 only has a single factor, which is 1. 2 only has 2 factors, which are 1 and 2. Okay, so that greatly reduces the calculations. Oh, whoops, I spoke too soon. I just realized I almost forgot. We also have to allow for negatives. So it's not quite as simple as it looks, but still, we should be fine here. Now, all right, so let's try this. P is a factor of 1. So P1 can be written as 1 times 1, or negative 1 times negative 1. So the factors of 1, because we're including the negatives, we're allowing, we're allowing for 1 and negative 1 then. So therefore, P must be either 1 or negative 1. Well, that means with 2, there's more possibilities. Yeah, you can see the number of possibilities starts to really pile up after a while. So therefore, with 2, which is Q, Q is a factor of 2. Which now, if you notice, we allow for these possibilities. 1 times 2 equals 2, but also so does negative 1 times negative 2. So Q must be 1, negative 1, 2, negative 2. So unfortunately, that leaves us with a lot of possibilities. So therefore, P over Q, ooh, this is going to be a lot, isn't it? So P must be 1 or negative 1. So we're going to have 1 over 1, 1 over negative 1, 1 over 2, 1 over negative 2. And then we have to repeat, oh my God. Yeah. But luckily, some of these might be duplicates. So what do we actually have here? Let me write the list down here. We got 1, negative 1, a half, negative a half. All right, we've already got this one. We've got this. Oh, all right. Well, it wasn't as bad as I feared because a lot of them are repeated. The 4 possibilities are 1, negative 1, positive a half, and negative a half. So what we have to do now, unfortunately, to find out which ones they are, if any, we have to plug those all one at a time into the original function. And what we're going to look for is, does it or does it not cause this function to be equal to 0? Now, in order to avoid wasting all day with this, I'm just going to show you the results. Okay, so we'll start with -1/2, and you can see by plugging that in here for x, the solution is not 0. So therefore, -1/2 is not a solution. All right, so we can rule that one out. Let's now try 1/2. Okay. What about when P over Q is 1/2? Let's try that. Oh, bad luck. Okay, did not work. 1/2 is not a solution, because otherwise this would equal 0. Okay, now we have to try positive and -1. So the next one is -1. All right, so let's just jump ahead a little bit. P over Q here, we're trying -1, and oh boy, no good. Well, now we got our fingers crossed that 1 is right, because that's all we have left. All right, so let's try 1. And P over Q is 1. Oh yeah, here we go. When we plug in 1 for x, we do get a 0. So therefore 1 is not only a solution, it is the solution. All right, so whatever this function is, it only crosses at the axis once at that point. And that's our solution. All right, so if you notice, I don't think this pops up on the, let me go at the second problem set. I may have thrown one of them in there, but that would have been about it. That is a very, yes, exactly. That's all you're doing. You're essentially saying, listen, here's the range of possibilities. Let's try them all and see if which ones work. That's really all you're doing. It's sort of it's sometimes called a brute force method, where you're just saying, here's all the possibilities. Let's just try them all. That's it. Try these, see which ones work, if any. It's kind of like, imagine yourself, you've got a combination lock, and you suddenly realize that you forgot it. But you think you know what it might be. Let's say you say to yourself, listen, it might be the 3, or how about, okay, forget that. That's an ancient example. Let's try a password. All right. You've got an account on your internet somewhere, on one of, let's say you've signed up for something or other, like a subscription to ESPN.com. And you go to it one day and you say, I want to read ESPN.com, but oh no, I forgot my password. And you realize, though, that even though you've forgotten it, you know that it's got to be your birthday, your name, maybe your nickname. Let's say there's only 4 things that it could be. So you try all 4 of them until you figure out which one lets you into that website. That's effectively what we're doing here, except that in our case, more than one of them might work. With the password case, only one of them can work. But the idea is similar. You've restricted yourself to the possibilities. You test them all to see which ones work, and then you're done. So you might say, what a bunch of work this is just to get a few solutions, but it might be helpful when the polynomial itself is extremely difficult to break down into factors. So in other words, there's at least a chance that this method could be faster than any other technique that you might try. So that's what it's for. Now, keep in mind, a lot of these techniques were developed quite a long time ago, way before computers were even thought of. at this point in time, you could just go get, like Symbolab could probably handle many of these. So, but you still ideally should understand what exactly is involved in finding the solutions to these polynomials. So even though the computer might be able to help you out, we still at some point have to understand what the computer is doing. So while it seems like a nuisance of a technique, it can be extremely helpful. All right, now in this last section, we're going to be looking at functions. Now here we have some kind of fun applications. You'll see what I mean when we get to it. And so there's just a couple more key ideas here that we want to look at in this chapter. And finally, so in other words, the most painful part is done here. Oh, yes, I wanted to open up the second problem set. Hold on. Here it is. No. There it is. I just want to quickly check. Oh, remember we were doing this last week, the vertex and all that good stuff, the axis of symmetry, the domain of range, the quotients. We did a lot of that last week, and the inverse. Okay, so this rational function thing that we're doing right now, although you should know it, if you notice, it's not on the problem set. And that means it's not on the test. Okay, I just want to mention that. This will not be on the test. It's good to know about it, but it is not on the test. It's just too messy. Okay, let's just say that that one is not going to be there. Some of this other stuff will be there, but anything that you don't find on the problem sets or in the sample midterm, which we'll be looking at next week, is not going to be on the test, and this is one of them. In fact, I think I may have taken out all three of these just because they're just a little too messy. You should know them or know what they are, but they won't be on the test. How about that? Does that sound like a plan? All right, but on the other hand, this part will potentially be there, rational functions, because this is important, and they have a lot of great applications, as we'll see in a few minutes. So here's what I think we should do. So it's getting late. Well, late, not late in the sense of the class being over, but late in the sense that we haven't had our break yet. So we'll do that. We'll wrap up this discussion, and then we'll dive into this practice problem set. And I think you'll find it to be pleasantly straightforward. And if there's still time left, then we can maybe take at least a peek at chapter 4. And by the way, chapter 4 will be a section where there's a lot of very interesting applications of it. Some of this stuff is more, useful in practice than others, but chapter 4, the exponential and logarithmic functions, they're very, very useful in practice. Okay, so we're going to pay especially close attention to chapter 4 because we'll get a lot of use out of it. And it's just interesting. All right, so why don't we knock it off here and have our morning break? I think we could use it after all that. Yes, we could. Well, the sample midterm will be the study guide and the notes. These slides, you can think of them as a study guide. All right, so all right, let's knock it off for a bit. And when we get back, we should be fully refreshed again and ready to dive back into the rest of the material, okay? All right, I guess we're ready. So back to 3B. Okay, so rational function simply means that it itself can be expressed as the ratio of two polynomials. Okay, and of course, when you see the word rational, the key detail here is the word ratio. And so that's where the name comes from. It's simply the ratio of two other polynomials. And that's what it means by a rational function. Now, let's look at some simple examples of this. And these are kind of fun. For example, and you've seen these problems before, a tank fills with water at the rate of 10 gallons per minute. So you've got, now this sounds like a high school physics experiment, doesn't it? You got water pouring in there. And then all of a sudden somebody decides to put sugar in there too. There's a spoon with sugar going in with the water. Okay. And so you're making a simple syrup, which means that it's water and sugar only. But the difference is that the water goes in at a rate of 10 gallons a minute, and the sugar goes in at a rate of 1 pound per minute. So at any given time, we should be able to figure out what proportion of the total is water and what proportion is sugar. So we started out, let's say, with 100 gallons of water and 5 pounds of sugar. Now, the following functions tell us how quickly the water fills into the tank. So you notice how we start with 100, and then we add 10 gallons per minute. T is minutes. Okay, T is time, but it's measured in minutes. 100 is the starting point. So you can see this is a linear relationship. 100 plus 10 more gallons for every minute that goes by is how much water the tank contains. And you notice the function is written as W of T, which simply means how much water is in the tank as a function of time, where time itself is measured in minutes that have elapsed since we started. At the same time, though, sugar, which is in pounds, the function there is 5 plus T because the initial value was 5. And then for every minute that goes by, we have 1 more pound of sugar. Okay, so we've got these two functions. Now, what are we trying to figure out here? Let's see. The concentration, that's what we're aiming for. In other words, the concentration represents the ratio of sugar to water. And so if we write it out based on these two functions, the concentration of sugar at any given time can be expressed very simply as the ratio of these two functions. And here's what I mean by that. It's equal to the amount of sugar at any given time divided by the amount of water. So because this function is the ratio of two other functions or two other polynomials, it therefore becomes a rational function. And here's what it can do for us. Suppose, and by the way, let's just think about this for a second. C of 0, in other words, the initial concentration can be calculated very quickly and easily as 5 over 100, or 5%. Okay, so initially 5% of the liquid is sugar, but what happens after 12 minutes go by? Let's find out. Oh, all right, here it is. So yes, the initial concentration is already here. It's 5% or 0.05. So what happens after 12 minutes? What does the concentration look like? So we're going to replace all those T's with 12. So instead of zeros, these T's will become 12s. And so you can see that we have now, remember, this function was originally 5 plus T. And this one is 100 plus 10 times T. So by replacing all the T's with 12, we have 17 over 220. So that means, whereas C0 was 0.05, That means after 12 minutes, it's 0.077, which means that the sugar is filling in faster than the water. And so as a result, the liquid is becoming sweeter, I guess you could call it, because there's more sugar in it after 12 minutes than there was initially. So like I said, this is a classic example of something you might have seen in high school physics. And I don't know what we're going to do with this information, but at least we can see that the result came about by solving a rational function. Okay, so rational function, again, simply means a ratio of two polynomials. And in a case like this, it proved to be exactly what we needed to solve for the concentration of the sugar in the water. All right. Now, just like many other cases, we would like to ideally be able to calculate the domain of these functions. And now remember what a domain means. The domain is what we are allowed to substitute into the function and still avoid having either division by 0 or possibly the square root of a negative number. So the domain, usually much if not the entire real number line could be the domain. In this case, it's kind of interesting because if you look at it carefully, the only value of t that would actually cause division by 0 would be -10. Now, but since this is a real example, this isn't really relevant because time obviously can't be negative. So what that means that in principle, given that time is what t represents, then all that really is relevant is positive or 0 for t. Okay, we don't want to substitute negative times into this function because they don't mean anything. No, this might be there. What's missing, if you come back here and look at this block of topics right here, let's go back. These three, these shouldn't be there. If they are, I'll take them out. I'm pretty sure that these were left out. Remainder theorem, factor theorem, and rational zero theorem. Everything else in here could potentially be on the test. And that includes what we're doing right now. All right, so in other words, starting with, well, everything before this, remember in the beginning, we were just introducing polynomials and looking at their properties, we did some division with them. And what else did we do? You might have to do the division. Remember, we were doing all these divisions. But here, these will not be on the test, these three, remainder theorem, factor theorem, and rational zero theorem. But now when we get past all this, we are now looking at rational functions. Now from this point on, this stuff might be on the test. So we're only excluding those three techniques for finding, okay, here it is, finding the zeros, these three, just because they're very, very, very complicated ideas. So it's good to have seen them, but they won't be on the test. All right. Okay. All right. So let's get back to this. So the rational functions, they're pretty straightforward. The domain normally, under normal conditions, the domain would be everything except -10. Well, usually the test itself tends to be organized according to topics. But, you know, there's no guarantee of that. They could be jumbled together, but they tend not to be. In other words, there's usually what I end up doing is I start with the questions from the beginning and work my way to the questions from the last topic that we covered. And so they're sort of in the right order, but I wouldn't guarantee it either. You know, in other words, don't assume that they're all precisely in the same order that we covered, but they will be more or less. Like, for example, in the beginning of the test, you'll mostly find chapter 1 questions and then chapter 2 questions. And then, you know, because it tends to work out that way because the later chapters are more complicated. All right. So anyway, but again, because this is a real world application, under normal conditions, you could make the case that the domain is basically everything from negative infinity up to, but not including negative 10. And then again, from everything starting, but not including negative 10 up to positive infinity. But because this is a real world example and t is meant to represent time, therefore the domain becomes just everything from 0 up to infinity. All right, so we do run into that sometimes. It's like, imagine if we were looking at dollars and cents. We can't obviously have negative dollars. So in a case like that, you would end up with the domain and a range, which have to be either 0 or positive. All right, so just remember that. Now this one, though, it's just x. We don't really know what x represents. So here, it should be clear that you may not allow, or you may not substitute either 3 or negative 3 into this function, because both of those would give us 0. So in other words, if you let x equals 3 or negative 3, then this will result in division by 0. So therefore, because we don't know what x represents, the domain would therefore be defined as everything except -3 and +3, which we could write in this way that we've been doing. And remember, the way these expressions are written, when you see a rounded bracket or a rounded parenthesis like this, that means we do not include that number. So the way this is written, it's meant to indicate that it's all real numbers except 3 and -3. So in English, you're basically saying anything can get plugged into this equation except 3 and -3. But the more formal way of writing it is like this. So you've got the entire real number line, except you have a hole here at -3 and +3. You may have seen it done this way in high school. All right, so these two numbers are disallowed. All the rest are included. All right, and so finally, the last topic in this chapter is something we've seen before, inverses and radicals. So we're basically going to do this again. So what we're basically doing is this. The quickest and easiest way to do this is to write it out like this. And now what we're effectively doing is simply swapping x and y and then solve for y. That's really, in a nutshell, what you're doing in these cases. So here, for example, we start with y equals 5x cubed plus 1. And then you'll see in the next slide that I'm going to rewrite it by changing the y to an x and the x to a y. And then I can rearrange it algebraically to solve for y. That's all I need to do. Now, sometimes it's a lot easier said than done. So I'm going to try to avoid the really incredibly annoyingly complicated versions. As far as I know, the ones on the test are fairly straightforward. I hope to avoid any that are unbelievably messy. But the logic is exactly the same every time. So in other words, given that this is where we started, we trade the x and the y. Okay, you notice how y became an x became a y. So now what we have to do is solve for y. Whatever we come up with is our inverse. All right, so what would you do here? Well, you could subtract the 1 from both sides. Actually, this is done in the next slide, so let's jump ahead to that. So now that we started with this point, we subtract 1 from both sides. Okay, and now what we'll probably do is divide both sides by 5. Okay, and now we just take the cube root And that's our inverse. So in other words, the original function was y equals 5x cubed plus 1. The inverse of this x cube root of x minus 1 over 5. And if you want to prove it, we're not going to do that right now. You can certainly prove it. Remember, to prove it, you must demonstrate two things. F inverse of x equals x, and F inverse of f of x equals x. Okay, so right now we're not doing that, but if you were to try to prove it, this is what you would have to do. All right, so don't worry, we'll see some of these on the sample midterm. Oh, actually, it looks like I did that in this. Oh, this is even better. So if you look at further ahead in the slides, it looks like we did go ahead and prove it. Nice. Okay, we could use the practice. So what we're claiming is that if this is our original function, f of x equals 5x cubed plus 1, then this is our inverse. So what you're going to do first, oops, sorry. Let's start with f of f inverse of x. That means you're going to take this function and all the x's will be replaced with f inverse of x. That's what you're trying to do. Okay, wherever you see an x, replace it with the inverse. Then you're just going to do a lot of algebra. Okay, and if you do it correctly, you should find that this expression reduces to x. All right, let's prove it. All right, let's jump ahead to the next slide. When you replace this f inverse of x with the cube root of x minus 1 over 5, and see how nicely this worked out. The cube root and the cube basically just offset each other. So you're left with 5 times x minus 1 over 5 plus 1. And just by, again, doing a little algebra, you can see that we do, in fact, wind up with x. So we proved one of the two things that we need to prove to show that we did, in fact, find the correct inverse. Now we need to go to the second step. So this time we need f inverse of f of x to be equal to x. All right, so let's show that on the next slide. All right, are we ready? Okay, let's jump ahead. So now this time, remember, we need to do f inverse of f of x, or show that this equals x. So what we're going to do here is go to the inverse and replace this x with f of x. All right, that's how this works. All right, so in other words, we're going to end up with f inverse of f of x equals the cube root of this entire expression, 5x cubed plus 1 minus 1 over 5. And now we want to make sure that this turns out to be x. If not, that means we've done something wrong. We don't like to do things wrong, do we? No. We want everything to work out perfectly. All right. So after following this step, what comes next? Well, you can see this is actually a very nice result because these ones drop out. And we've got the cube root of 5, x cubed over 5, which means these drop out. And so we're taking the cube root of x cubed, which of course is just x. And so we're done. We've proven what we needed to prove. We showed that f of f inverse of x equals x. We've proven f inverse of f of x is x, and these combined prove that f inverse of x is indeed the cube root of x minus 1 over 5. And we're done. So we not only found the inverse, we proved it. Now, if on the exam, if it doesn't specifically say to prove that you found the correct inverse, you don't have to, but you might want to do it anyway just to make sure that you haven't made any mistakes. All right, now one last topic here, and this is very quick and easy. We're going to introduce another type of function which you're very familiar with anyway, and that's called the radical function. Okay, so in this context, the word radical simply means that we're taking roots, or you can think of this as raising something to a fractional exponent. All right, and so for example, a radical function contains the square root of x, the cube root of x, et cetera, et cetera. So this could be construed as a radical function because it contains a cube root. Okay. And that's all you need to know. Okay. As long as there's a fractional exponent somewhere, okay, or a root, then you have what's called a radical function. Okay. So this is therefore a radical function. And that's all you needed to know. All right. Now, before we go to the practice problems number 2, I just want to quickly review what we did last week in the first half of this chapter, our discussion about the vertex of a parabola, okay? Because it's been a week, which is, of course, a constant problem in this class, that every time we do a topic, you know, let's face it, you know, it's been a week since we thought about this, and that's a long time, especially when you're learning math. So we're going to go back to chapter 3a and just quickly review everything we did involving vertices or vertex, the vertex. In other words, vertices is the plural of vertex. You might recall we decided that, you know what, maybe we should introduce the key characteristics of a parabola and understand what they mean. So the key characteristics of any parabola are, number 1, the vertex, number 2, the axis of symmetry, number 3, the zeros, or they're also known as solutions, and number 4, the y-intercept. What exactly is the vertex again? Well, if you recall, the basic shape for any parabola is either this or this. It's the highest or the lowest point. Okay, the vertex itself is either the maximum or the minimum. So here the vertex is this point. And here the vertex is this point. Yes, go ahead.
Whoops, sorry, my headphones were muted. The thing that I struggled with on the assignment was like I understood the vertex and could recognize it in the vertex form, but didn't make the connection between the vertex and finding the point that makes the axis of symmetry happen.
Oh, the axis of symmetry has to cut through the vertex.
Yeah.
So,
But like in this video I watched, he like had 2 points, like one above the vertex or below the vertex.
really?
And I was like,
Okay.
didn't know where he was getting that point. Yeah.
Ooh, I can't imagine why they would want 2 points.
Okay, so maybe I was just like misleading myself somehow.
Yeah, I haven't seen that video. I don't know what they were doing. Maybe
It was by like Brian McLogan on YouTube, but so then when the assignment asks like find vertex, min or max, and axis of symmetry, are those all the same point?
well,
'Cause Min and max
Yes.
are the vertex, and if axis of symmetry just runs through there.
That's exactly right. In other words, the vertex tells you where the axis, because you can see visually by looking at this thing. But the point of it is that the axis of symmetry is a vertical line, and it is technically not a function. It's x will equal some constant k, let's say. And so if you know the vertex is h comma k, then the axis of symmetry is nothing. Actually, no, it's
The constant y.
it's the x. Actually, you know what? Let's wait till we get to that point. I don't want to write the wrong thing here, but just note that the vertex is the minimum or maximum point, and the axis of symmetry is the vertical line that cuts through that point. So if let's see, let me jump ahead a little bit here. H comma k. All right, so that was correct. H comma k is the vertex. And the axis of symmetry is therefore, and you'll see down here somewhere, okay, so here's how they explained it. And I just wanted to make sure I don't say something different than I did last time. If that's the case, now remember, the quadratic formula is designed to help us find solutions for this parabola. So the derivation of the formula for h is coming, actually, believe it or not, from the quadratic formula. And we're not going to go through that, but if you really wanted to, you could sit down and prove that this must be correct based on the quadratic formula. But the formula for h is negative b over 2a based on the equation of the parabola, right? It's negative, it's negative b over 2a. And you recall that because this is a parabola, the equation must be f of x is ax squared plus bx plus c. That's where the b and the a comes from. And then the axis of symmetry, you can think of it as x equals h, or, hold on, the axis of symmetry is a constant value for x. You can think of it as x equals h, or x equals minus b over 2a. So for example, if h equals 3, then x equals 3 would be the axis of symmetry. All right, so in other words, if in this case, if h equals 3, then our axis of symmetry is simply the vertical line, x equals 3. So in other words, these two are directly related to each other because, as you can see, because the curve is symmetrical on either side of this vertex, the axis of symmetry is just the straight line that separates the parabola into the two halves, the left side and the right side.
So how would you find the y then? Like if we know x is 3, how do you find the y if it's not exactly at 0, you know?
Then the k would simply be obtained, in other words, the y value, by plugging in h into the original function. So you would have a h squared plus b h plus c. Okay, in other words, whatever h is, you can find k by plugging h in to the original function. Okay, so let's look at some examples again. You'll see what I mean. All right, so let's run through this one more time. So the vertex, like we said here, it's either the maximum or the minimum. Now, because parabolas are quadratic functions, they are guaranteed to have a minimum or a maximum. The question is, where are they? Now, they won't have both. They cannot have both. It's either a minimum or a maximum. And what determines that is the sine of A. And you might recall that when we draw a parabola, how do we know if it faces up or down?
If A is greater than 0.
That's right. Up means A is greater than 0. Okay. So remember, always the function itself is ax squared plus bx plus c. So upward, when it faces up, A is positive. And when it faces down, like you said, that means that A is negative. But this also implies that the vertex is a minimum, or is the minimum point, h comma k. And over here, that guarantees that the vertex is the maximum point, and it's still called h comma k. It's like two mountains. Here we're at the bottom of the valley, I guess, and here we're at the top of the mountain. That's how you can think about it. And so whichever one it is will ultimately depend on the sine of A. But the axis of symmetry, in either case, is the line, the vertical line, x equals h. And since h is found by finding negative b over 2a, that means that x also equals x negative b over 2a. Now the solutions are coming from the quadratic formula, of course. Those are the solutions right here. All right, the solutions would be, we'll call them x1, x2, x1, x2. And the intercept, the y-intercept, somewhere along the way, and this could coincide with the vertex, the parabola will cross the vertical axis. It has to at some point. And that's easy to find. What you have to do is set the entire equation equal to 0. In other words, you set x equal to 0. Okay, so in other words, wherever x is 0, that means you're on the vertical axis. Whatever the value y is, that's going to be the the y-intercept. And in fact, you can see, because of the way this thing is written, that's actually going to equal c. The constant has to be the y-intercept. All right, now that could or could not, it could coincide with the vertex, but it doesn't have to. All right, so let's just quickly run, there's a couple of good examples in here. Let's just quickly run through them before we get back to the problem set. So we know that if A is positive, the parabola opens upward and the vertex is therefore a minimum. If A is negative, the parabola opens downward and the vertex is now the maximum. So the vertex, now this part, I would say this part is absolutely necessary. This is just an equivalent way of looking at the parabola. Once you have this information in place, it's very easy to spot the vertex, HK. But it isn't really necessary, I don't think. Well, let's just say, let's follow the approach here. We start with the function, and of course, remember, as always with a quadratic formula, the function is written traditionally as f of x equals ax squared plus bx plus c. And therefore, in this case, a is 2, b is negative 6, c is 7. And this guarantees, because a is positive, we'll have an upward facing parabola. Now, it looks something like this. Now, this is the one, I remember I was annoyed with this one because in Excel, it's very hard to see where the vertex is. So we went to Symbolab, said, all right, Symbolab, here's a job for you. Yeah, that's a nice thing about this, because a lot of times it's really tricky to visualize what these functions look like. All right, so what do we have here? It's 2x squared 2x squared minus 6x plus 7. Whoops. Plus 7. And we graphed it out, and we discovered, oh, it's taken a while. Surprisingly long time. It's usually pretty fast, isn't it? Yes, it is. Wow, what's going on here? That's a really simple case. There we go. Okay. And here we go. It looks like this. So, oh no, wait a minute. Oh, I see. Okay. That's a different example. Okay, I get it. I wasn't sure. I've forgotten exactly how this thing works. In this case, you can always find the axis of symmetry in the vertex, but I would remind you that when the parabola doesn't actually touch the horizontal axis, the solutions will be imaginary. But in this example, we're not looking for the solutions anyway. So all we wanted to know is, where is the axis of symmetry? And so that's the formula, minus b over 2a. The vertex, though, is easy to find. Now, you don't have to write it out in this form. All you have to do is this. We need to know, okay, let's try that again. The function is y equals 2x squared minus 6x plus 7. So if you want to find the vertex, all you have to do is do it. You can do it in 2 stages. H equals negative b over 2a. Oh, really? Oh, I'm sorry, I didn't notice. Okay, go ahead, Solomon.
Oh, sorry. Oops. I think I just left my hand up from when I raised it like a while
okay.
ago.
Oh, I see. All right,
So it's all
that's
good.
fine then. All right, no
Thank you, though.
problem. Not a problem. By the way, I tell you what, if there's one person on the face of the earth who does not know these abbreviations, believe me, take my word for it. Do not assume that I know what LMAO stands for. Okay, I do not. I promise you, I do not know what that means. All right. Oh, all right. See, I had no idea. The only one I know is LOL. I've heard of LOL, and that's it. That's as far as it goes. All right. I have no idea what any of the others mean. Do not use them, because I will not understand you. Just assume that I don't know. It's like with the faces, these guys. I don't use them because why? Why would I use these little faces? I don't get it. I don't use faces. In fact, I try not to use text whenever possible either. So assume that I'm 20 years behind the times when it comes to technology, because you're probably right. All right, anyway, so this is a 2-step process to find the vertex. H equals negative b over 2a. Now, clearly in this case, you can see that a is 2, b is negative 6, c is 7. When you plug in minus b over 2a, you get 3 halves. So now you know that h is 3 halves. K is...
Wait, here's like a little question. So like minus b over 2a would, I don't know why I'm confused about this exactly, but we have this negative 6, so would it be 6? Would it become 6 over 2a? Or would it stay negative? It stays negative.
In this
I
case,
see.
the negatives cancel out. So you end up with 6/4. That's why this is happening. Remember,
Okay,
this
the
negative
negatives do cancel out.
Right, exactly. So it is positive 3 halves. Now, to find the k, just go ahead and plug in 3 halves into this equation. F of 3 halves would therefore be 2 3/2 squared minus 6 times 3/2 plus 7. Okay, I'm desperately short on space here. And that would give me 2 times 9/4 minus, this is 18/2 plus 7. Now, what a mess. 18/4 minus 18/2 plus 7. Let's convert these all into quarters so that we have a common denominator. And so I'm going to have 10/4 or 5/2. This is K, by the way. So H, just to summarize, H is 3/2. The corresponding K is 5/2. So the vertex is the point 3/2, comma 5/2. I don't have to write this expression to come up with that. I can, but it's not necessary. The advantage of having it in this form is that it's immediately obvious, though, what the vertex is. Now, if we go back to Symbolab, it probably has this identified in there somewhere. Let's look at this. It has everything here, even whether you ask for it or not. All right, see now, it's calling it a global minimum, but it means the same thing, 3/2, comma 5/2. That's the vertex. That is the minimum point on the entire parabola. Now, this implies then that the axis of symmetry is the equation x equals 3/2. Now, they don't show that in Symbolab, but I have it here. Yeah, I mean, again, Excel is kind of awkward to work with sometimes, but this is the equation x equals 3/2. And it's just simply a vertical line that cuts through the axis, the vertex rather, which if you recall is 3/2, comma 5/2. And that divides the parabola in half. The left-hand side is an exact mirror image of the right-hand side. All right, the zeros or solutions just come from the quadratic formula, and the y-intercept, let's see if we can find the y-intercept. That would simply be the point where x equals 0. So you'd have y equals 2 times 0 squared minus 6 times 0 plus 7 equals 7. So the point, it's really hard to see on this thing. Right about here, I guess, the point 0, comma 7 would be the vertical intercept, because x is guaranteed to be 0 on the vertical axis. So the question is the value of y. It's probably, let me see if I can, right here, it should be labeled, yeah, 0, comma 7 is the y-intercept as it's called. And how did we find it? By substituting zeros for the x's. And because it's a quadratic equation, effectively all you're really doing is saying that the y-intercept occurs, just in general, where x equals 0 and y equals c, the constant in the equation. All right, I think we've refreshed our memories enough to go back to the problem set now. Yes, we have. We've done a lot of refreshing here. So let's take a peek. Now, this one does explicitly ask you to rewrite in this form, but that's easy. Basically, all you have to do is solve for the vertex and then plug it into what you're seeing here. So let's do it. So here, a equals 1. Should do this first. C equals 32. And remember, h equals negative b over 2a, negative 12 over 2 times 1, equals 12 halves or 6. K is f of h, which means in this case, f of 6, which means 6 squared. Right, remember the function is x squared, so it's 6 squared minus 12 times 6 plus 32, which equals 36 minus 72 plus 32 equals -4. Okay, so the vertex is 6 comma -4, and this expression up here can therefore be rewritten as, now remember a in this case is 1, x minus 6 squared minus 4, or you can just rewrite it as f of x equals x minus 6 squared minus 4. So in other words, this expression and this expression mean the same thing. It's just that this is written in vertex form. Right, I don't know about you, but I prefer it this way, but for certain applications, this would actually be more convenient. Wow, that was a lot of steps. All right, so we got a few more to go, but the logic is pretty simple, I think. All right, so here's another one. And so here we can see that A equals 1 again. B is positive 2, and C is -3. So let's first figure out the value of B. -2 over 2 times 1 is -2 halves, which is -1. And then once again, remind ourselves K is f of h, or f of -1, which means, so you've got -1 squared. The function is right here. -1 squared plus 2 times -1 minus 3 is 1 minus 2 minus 3, 1 minus 5 minus 4. So the vertex is the point -1 minus 4, and the equation in vertex form is therefore, and yeah, let me just copy this one more time so you can remember what this function looks like. No, not yet. I'm still looking into it. Anyway, so A is, as you know, from the beginning 1, so we don't even need to write it there. It's just x minus 1. Oh, we have to watch it here. All right, let's do this. Let's put the 1 out here. That's A. X minus -1 squared minus 4. Therefore, you can just write it as x plus 1 squared minus 4. If you have any doubts about whether you've done it correctly or not, you can just expand this with FOIL, add the -4, and you should end up back where you started, right here.
I don't know exactly what I was doing. I got f of x equals x plus 1 squared minus 3. Oh wait, no, I see where I went wrong.
Oh, okay, good.
When I subtracted the 1 from like both things, I forgot to subtract it from the 3. So I kept my -3 instead of making it -4.
Okay, all right, very good. All right. Now for this one, now you notice this one's interesting because C is 0. Now that won't affect H. So let's see, we got minus 1 over 2 times 1 equals 1 over 2. We can just leave it like that. And then, as you know, K is f of H, or f of a half. You could write that as 0.5 if you want to. Well, I don't think it matters. All right, so you've got 1/4 minus a half, or you can think of it as 1/4 minus 2/4, which is minus 1/4. So the vertex equals a half comma negative 1/4. All right, and so therefore, what we're going to do is find the vertex form of this equation. Let me just copy that again one more time. A, remember, is 1. X minus, now H is 1/2. We square that. We add, well, actually, then we'll subtract 1/4. And we can just write it as X minus a half squared minus 1/4. And that's it. That is our vertex form. All right.
Wait. I'm a little bit confused. Like, so I got, for that one, I got f of x equals x minus 1/4 squared.
Oh, but remember, it's X minus H.
X minus h.
Right. This is the actual formal definition. This is supposed to be H right here.
So basically, I didn't do it all the way, like, because I didn't solve for x.
Well, I think you just substituted the wrong thing in there. Did you
Okay.
get K is negative 1/4?
Yeah, I got negative
Oh.
1/4, but I don't think I understood, like, what variable I was solving for. You know what
Oh.
I mean?
All right. Well,
Yeah.
just think of it this way. First, always do H first. That's very simple based on the definition of this equation. And then what you're basically just doing is you're substituting this H into the original function for all the X's and coming up with the solution. And so in other words, if I put a half in here for X squared and a half for X, I'll end up with negative 1/4.
Gotcha. Yeah, I learned it a different way yesterday. I like did it by, like, you take, see, I'm just looking at these notes. What two numbers multiply to give me 36 and to give me negative 12? That's for one. Or no,
Why
that's
is
just
it-
an example problem.
Oh.
And so then I like found those. Do you see what I'm saying? Or have you done it that
No,
way?
I'm not familiar with that technique.
Okay.
Is that
It was
something you did? Well, as usual, you should do whatever you're comfortable with, but I don't know. I think this technique is pretty straightforward.
I like this too. This is making more sense to me than what I was trying to do yesterday.
Uh,
Like the steps were, I have them more
Excuse me.
clearly written out here, is like group the like 2x squared and 10x term, factor, so you get a equals 1, find value of c that completes the square,
Oh, come
and
on. No,
add and
don't
subtract
mess
value
around
of
with that.
c factor to a binomial squared.
You're just grossly overcomplicating everything when you do. Just do what we're doing here. I think you'll find it's easier.
So far, it seems more straightforward than this.
That's the problem with these so-called shortcuts. Sometimes they can lead you down a path that makes it even more annoyingly confusing. I don't see, every shortcut is different because you're basically changing the way you're looking at this equation. And I don't know, not all shortcuts to me make sense. And so if the basic technique works well, you should probably just stick with it. You know, shortcuts are fine if you have an unusually complicated situation, but most of the time you're better off probably with the original technique. So, you know, and especially after you've done a few of these, I mean, this H formula couldn't be much simpler. And all then you're doing is really plugging this 1/2 into this equation and replacing all the X's, and whatever you get is your K.
Gotcha.
As scary as it looks, really, it's not that complicated. But all right,
So-
let's just do one more. All right, go ahead. Yes.
It's solve for H, plug H in to get K. Those are
Yeah,
like the two
that's
steps.
it. That's literally all you're doing. In fact, if you want to reduce this to English, just solve for H with H equals negative B over 2A, which you know what that means. And then plug H into the function for X and solve. And you're done. And this gives us K. And that's it. That's all you have to do. All right, so let's do it here. Let's prove it. So A equals 1, B equals 5, and C equals -2. H equals negative B over 2A. I'm sure you have this formula memorized by now anyway. Minus 5/2. So K is F of H, which means F in this case of minus 5/2. So you go back to the original equation, you've got minus 5/2 squared. Negative 5/2 squared. Plus 5 times minus 5/2 plus minus 2. All right, hold on one second. All right, so that means now when you square negative 5/2, you end up with 25/4. Here you've got minus 25/2 minus 2. So if we convert these all into quarters, you'll have 25 over 4 minus 50 over 4 minus 8 over 4. That's going to give me minus 33/4. Ooh, wow, what a mess. Oh no, this is just practice. Yeah, don't send anything to me. Yeah, 100%. This is just for your own practice. Okay, so therefore, so the vertex, okay, the vertex is therefore, of course, minus 5/2 comma minus 33/4. And so the function that we need now to write this into vertex form will be, now A, remember, is 1, X minus 5/2 squared minus 33/4 because K is negative, or you can simply rewrite that as X plus 5/2 squared minus 33/4. All right. Now what do we do? I see. We have some quadratic equations, and we're going to find the minimum or maximum point. Now, you notice when it says the minimum or maximum point, that is just another way of saying you're going to find the vertex, because the vertex is the maximum or the minimum point. And of course, then you can simply find the axis of symmetry with our formula. Okay. All right, so remember H is negative B over 2A. And then K is F of H, or F of negative 5/2. So we'll have 2 times minus 5/2 squared plus 10 times negative 5/2. We got to watch out with this one with all these negatives. And so 2 times, now negative 5 halves squared is positive 25 fourths. Then we'll have minus 50 halves plus 12. All right, let's clean this up a little. 50 fourths minus 50 halves plus 12. Now, what I recommend here is that we convert everything into fourths to have a common denominator. So that's minus 2 fourths or minus a half. So the vertex is h comma k, which is minus 5 halves comma positive or a negative 1 half. And therefore, the axis of symmetry is simply x equals negative 5 halves. You don't have to solve for it again. It's just the h. Now, I think since we have access to it, we may as well go take a peek at this in Symbolab just to see what it actually looks like. And you'll see that it lines up with what we've been doing here. So let's go take a shot at that. Good old Symbolab. What would we do without it? All right, so this time we need 2x squared plus 10x plus 12. Okay, now the vertex is supposed to be minus 5 halves minus a half. And in fact, there it is. Now, again, they're calling it a global minimum, but it means the same thing in this case because the vertex is a minimum when the parabola faces up. So we've got minus 5 halves comma minus 1 half. Excellent. That means we've done it correctly. Woohoo. And you can now see what it looks like. And if furthermore, you were asked to find, for example, the y-intercept, it's right here. You can, and if you were asked to find the solutions, they're right here. So that helps a lot. All right, what about this one? So after a while, you start to say, you know, these aren't really hard at all, are they? No. It's just, you know, like everything else. After a while, you start to get the hang of it. Start to see the logic behind what you're doing. And all of a sudden, before you know it, everything makes sense. The 10 fourths are 5 halves, and k therefore is f of h, f of 5 halves, 2 5 halves squared, plus, or minus rather, 10x plus 4, 2 times 25 fourths, minus 50 halves plus 4. We get a lot of halves and quarters for some reason in these. I don't know why. It's just a coincidence, I think. So we'll reduce everything to fourths. So you've got minus 34 fourths or minus 17 halves. Okay. So the vertex is h comma k, or 5 halves comma negative 17 halves. And the axis of symmetry is just x equals 5 halves. Because I've already solved for it. Remember, x is just the vertical line whose value equals h. All right, so that's what you had to do for that one. All right. Now, number 7. Now, this one's different because this is the first time in a while that we've had a parabola that faces downward. You can tell just by looking at it. We don't need to graph this one, but this one we might want to graph. In fact, why don't we do that first? Minus x squared, just to see what it looks like. All right, so what is it? Minus x squared plus 4x plus 3. All right, so the graph is here. And what do you know? It does face down. And now, well, we're going to cheat a little bit here. The answer is 2 comma, that's the vertex, 2 comma 7. We're going to prove it though. All right, since we already know what the answer is, we're going to prove it now. All right, how do we do that? All right, well, let's see, A is -1, B is 4, and C is 3. So therefore, H equals minus B over 2A minus 4 over 2 times -1. So we've got minus 4 over -2, which is 2. So f of 2 is minus 2 squared. Oops. Plus 4 times 2 plus 3. This is minus 4 plus 8 plus 3, which is 7. Yeah, so the vertex, as we just saw, 2 comma 7. And the axis of symmetry is equal to x equals 2. Okay, so that's what we saw in the graph. 2 comma 7 is the maximum point, or the vertex, and we're done. Oh, now the next one looks pretty frightening because you've got A is 4. All right, so usually the higher the value of A, the more messy the answers become. That's just an unfortunate reality. All right. So H is -1/8. K is f of H equals f of -1/8, which is 4 times -1/8 to the second power. Plus -1/8 minus 1. So minus 1/8 squared is actually 1 over 64. So let's convert everything into 64ths. We might as well leave this as 4 over 64. 1/64th, 1/8 is the same thing as 8 over 64. So we're going to have minus 70, wow. 76 over 64. Luckily, this can be reduced a little bit. If you divide, oh, wait a minute, maybe not. Oh, no, sorry, this is not right. It's not 76, it's minus 68 because this one is positive. 4 minus 8 is minus 4. Yeah, that's better. And this one can then be reduced to 17, negative 17 over 16. Much better. So therefore, the vertex is negative an eighth, comma, negative 17 over 16. And of course, the axis of symmetry is x equals negative an eighth. Ooh, I was afraid of that. Yeah, that high value of a means that the answers are a little bit messier, but we did it. Okay. Now, here's some that you might have forgotten about. Let's go back to the slides for a minute. This is something we're going to be looking for domains and ranges. So you might recall that for quadratic functions, there's some simple formulas to help us find these. All right, so let's go back and revisit what we were doing here in chapter 3a. There it is. So the domain of a quadratic function, each time we don't have anything to worry about. For each quadratic function, the domain is very simply all real numbers. There's no number that can be plugged in here that could cause division by 0. So we're fine there, but the range depends on the sign of a. So when a is positive, this is what we're looking at. And by the way, if you notice, negative b over 2a is h. So you could think of that if you wanted to as f of h and infinity. It means the same thing. But that just keeps showing up over and over again, doesn't it? And when we have a negative result or negative a, it's the same idea. It's just that you're reversing the two. And again, we note here that you could write this as negative infinity, comma, f of it negative h. It's negative h. No, sorry, it's positive h. So, wow, nice. So for number 9, right off the bat, we know that the domain is simply the range from negative to positive infinity. Now, since, oh, you know what we should probably always do before we do anything else? Just note the values of a, b, and c. And so since a is positive, the range is, so we'll use this expression. Okay, now this is the challenging part. So we know that h equals negative b over a is minus, oh, I made a typo here. This should be b. Minus 6 over 2 times 1 is minus 6 halves, which is minus 3. F of minus 3 would be negative 3 squared plus 6 times minus 3 plus 4, which is 9 minus 18 plus 4, which is minus 5, it looks like. Yeah, that's right. So that means that the range is everything from negative 5 up to positive infinity. It's in other words, no matter what number you plug into this function, you'll never get a y value below -5. Now, luckily, once again, we can consult with Symbolab to prove this. We're going to visually look at this function and say, well, why is this the case? Well, you know what? Well, we're going to find out. And you'll see something interesting here. So the function here is, x squared plus 6x plus 4 all right. Now look, the global minimum is -3, -5. So in other words, there's no y value below this that the function can assume. The range, therefore, starts at -5 and works its way up to positive infinity. And if you notice, h is the -3, k is f of h, which is -5. So the range could be thought of as k, comma, infinity. Now that we know what a vertex is, you can think of it as simply k, comma, infinity. In other words, k is the y value for the vertex, and therefore the value must be anything from k up to infinity. Wow. So that's how come it turned out this way. It's just that point, remember, since this is the minimum, it stands to reason that the range starts at k and works its way up to infinity. How do you like that? It's amazing how this stuff ties together like this. All right. So let's see. Oh my God, how many more do we have? Oh, this will be fun. Division. Remember we did division last week? Was that fun? My thinking is that you're going to say no. So I'll tell you what. Now, the exam won't be for a while anyway. Why don't we do this? We're largely done. We've completely done the first problem set. We're largely done with the second one. Why don't we do this next week? Let's wrap this one up and then do, I'll have the sample midterm ready by, let's say, tonight or tomorrow. And it will be just essentially everything we've done up to this point, but that means it also includes the first 2 chapters. It's not just this chapter. So why don't we agree to do the following? For next Wednesday, we'll finish this second chapter 3 problem set and the sample midterm. And then you'll be 100% ready for the actual midterm, which I will post. And then you'll have, let's say, a week or so to finish it at home with all your notes and all your slides and everything in front of you. And you can send it back to me by taking pictures of everything you've done with your camera as if, well, I mean, obviously if we're in a classroom, you'd write everything in a blue book. Instead, you'll be taking pictures of what you're doing and emailing them back to me. And that's how we will conduct our midterm. All right. So you'll have plenty of time to do everything, and you'll have all your notes right in front of you. So you should have no trouble whatsoever. And in addition to that, if you get stuck, you can always send me questions by email. Not that I can give you the answers, but at least I can help you out. All right. So let's stop here, and we'll just remember to finish this up next week and the sample midterm. All right. And then if there's still time left over, then, like I said, we'll start to look at chapter 4. All right. So are we all set? Everybody's happy?
All set.
Good. All right. I'm sure you're tired by now anyway. I mean, that's a lot of math for one day, especially
just to
early
like
in the
make
morning.
make sure we have sample midterm on Moodle right now and then midterm
No.
next week.
It's
Sorry.
no, well, the sample midterm is almost ready. I've got to make a few changes to it. It should be ready by tonight. I'll
Okay.
post it up there later on. So you'll have about a week to work on it. And then you make sure you finish up this one, and then we can carry on from there.
Okay, so this week work on sample midterm. Next week the midterm is assigned.
Correct. And you'll have a week after that to do it.
Awesome. Thanks so much.
All right. You're welcome.
Thank you for your time, Professor.
All right.
Very
See you
much
later.
appreciated.
Thank you, Professor.
Bye.